Good afternoon, ladies and gentlemen. It is my great honor to welcome you to the 13th Gerhard Ertl Lecture. My name is Gerhard Meyer, and I am the Managing Director of the Fritz-Haber-Institut of the Max-Planck Society, and I extend a warm welcome, first and foremost, to my predecessor, Professor Gerhard Ertl, Nobel laureate and the reason why this award came to existence, as well as to Professor Ulrike Diebold, this year's award winner. I would also like to welcome Dr. Detlef Kratz, BASF, Professor Christian Thomsen, President of the Technische Universität Berlin, Professor Günther Ziegler, President of the Freie Universität Berlin, and Professor Sabine Kunst, President of the Humboldt-Universität zu Berlin, as well as the Vice President of our section of the Max-Planck Society, Professor Klaus Blom. We have also been joined by the award committee, comprised of jurors Professor Joachim Sauer from the HU, Professor Matthias Dries, TU, and Professor Eckhard Rühl from the FU, as well as the Fritz-Haber-Institut's Board of Directors. I am currently standing in the library of our Berlin Institute, located in the oldest building on campus, dating back to 1911. It is a place vibrant with the history of the Fritz-Haber-Institut. One can practically feel it. This building has seen it all. The last German emperor, Kaiser Wilhelm II, came here to celebrate the opening of the Institute in 1912 through this door. Albert Einstein worked here for a while shortly after that, and no less than 8 Nobel Prizes in physics and chemistry were subsequently awarded to members of this institute. The most recent one was awarded to Gerhard Ertl in 2007, who was director at the FHI almost 20 years. This prize holds a special significance for us here at the Institute because thanks to Gerhard Ertl's research, the work of Fritz Haber was finally able to come full circle. The methods for studying surface chemical reactions that Ertl developed enabled him to map out previously unknown details of the Haber-Bosch process, in which nitrogen in the air is converted to ammonia via an iron catalyst. The Haber-Bosch process continues to be of great importance in the production of artificial fertilizer, and Fritz Haber was awarded the Nobel Prize in Chemistry for this achievement. The correlation between our first and most recent Nobel laureate is the epitome of scientific work. The knowledge it produces comes not from one individual, but from a community, a network of scientists connected through space and time by their shared goals. Scientific work is always collaborative. Even if the collaborators work at different times in history and never meet in person. Their work builds on that of others, will in turn be built on in the future. The Fritz-Haber-Institut, the 3 Berlin Universities, and the Catalysis Research Consortium UNISYSCAT have, with the generous support by BASF, established the Gerhard Ertl Lecture Award in 2008 to honor the great achievement of Gerhard Ertl and to recognize the work of other exceptional researchers in Ertl's line of research in physical chemistry and chemical physics. Its aim is to honor, but also to connect, to bring together the community focusing on catalysis and surface science. It has been a trying year in many ways. But I am glad that the global situation has inspired us to open up this event, to come together virtually in much bigger numbers than would normally have been possible. It is my great honor to welcome all of you watching from your offices or from home and to introduce this year's winner of the Gerhard Ertl Lecture Award, Professor Dr. Ulrike Diebold from the Technische Universität in Vienna, Austria. Professor Diebold is a distinguished physicist who has considerably advanced the fields of surface science, materials and physical chemistry, and condensed matter physics. Specializing in surface structures and molecular reactions at metal oxide surfaces, he has added countless invaluable scientific insights to this field close to 30 years. Ulrike, I would like to once again congratulate you. I'm very much looking forward to your lecture, Oxide Surface Science, Chemistry at the Atomic Scale. After Professor Diebold's lecture, there will be a question and answer, and you are all encouraged to submit any questions you might have during the talk. After the presentations, I get these questions then presented on the screen in front of me, and I will read out these questions to Professor Diebold, who can then answer. If you want your name to be indicated when you ask a question, please do so, so that I can also forward that. But before we get to hear and discuss your work in the following Q&A, Ulrike, I would like to give the floor to Professor Christian Thomsen, President of the Technische Universität Berlin, this year's host of the Ertl Lecture, as well as to Dr. Detlef Kratz, President of Process Research and Chemical Engineering at BASF.
Dear Professor Meyer, dear Professor Ertl, dear Professor Diebold, dear colleagues from the jury of Technische Universität, Freie Universität, and Humboldt-Universität, dear colleagues presidents from these two institutions. I welcome you very much to this Gerhard Ertl lecture that we're having today, and we're very proud to have you, Professor Diebold, as a speaker here. To say a few words about the Gerhard Ertl lecture, we've been having it for 12 years now, and we've had excellent speakers, just like we're proud of having you today here, Professor Diebold. The work on chemistry has been in particular strong in Berlin because of the center, the cluster of excellences that we've had. There's one Uni CAT, which has been going on for 12 years before, and now recently Uni Siscat in the most recent round of the excellence strategy began. Uni Siscat stands for Unified Systems of Catalysis, and the idea is to work and research on the utmost importance of catalytic processes, not only in research but also in economy. We see that, among others, with participation of BASF, and I welcome very much Professor Kratz here. BASF is interested in the economic usage of catalytic processes, and many of the economic values that are generated in Germany and the world, to say, are based on catalytic processes. We're also very proud to have Professor Ertl here. You've got the Nobel Prize in 2007, I believe, and the Berlin Universities are proud to have you as an honorary professor. So I'm looking very much to the upcoming lecture by you, Professor Diebold, and thank you again for all of you being here. Thank you.
Okay, so after these introductory words, I now give the floor to Dr. Kratz, speak out the laudatio.
Thank you very much. Glad to do so. First of all, thank you for the professor title. Just as a point of correction, of course, I'm aiming at it, but there are so many professors already on the call here. So I think industry and academia work together, and that's very good. So dear Professor Diebold, dear Professor Ertl, dear Professor Thomsen, Professor Meyer, ladies and gentlemen, and everyone who is dialed in today, it is of course a great honor for me to introduce our speaker for this year's Gerhard Ertl Lecture Award ceremony, Professor Ulrike Diebold from the Technische Universität Wien. And I'm delighted that you, Ulrike, are the 2020 recipient of the Gerhard Ertl Lecture Award. Now, it's obviously unfortunate that we could not meet in person this year, as the corona pandemic forces each and every one of us to stay at home. I would have loved to have been in Berlin, but now I have to make do with my home office. But let's make the best out of it and connect to this virtual event. And connection was already mentioned by Gerhard Meyer, that this is, I think, the essence of what it means in science. Now, the jury has selected Ulrike Diebold in recognition of her pioneering work and great accomplishments in the fields of surface science, materials and physical chemistry, and condensed matter physics. And for more than 30 years, she has proven her knowledge on surface structures and molecular reaction at metal oxide surfaces, and has added countless invaluable scientific insights to this field. Ulrike is a distinguished physicist, as is evidenced by her exceptional publication output of outstanding scientific quality, and therefore she has received numerous awards in the course of her career. Now, ladies and gentlemen, I do want to stress again what was already pointed out, that before I introduce Ulrike and her achievements, let me start by telling you a little bit about the award itself and how BASF is involved with it. The Gerhard Ertl Lecture Award was first presented in 2008, as already pointed out, by a number of institutions: the Freie University of Berlin, Humboldt University, the TU Berlin, the Fritz-Haber-Institut, UNICAT, and BASF. And it is dedicated to one of the most prominent scientists in the field of surface chemistry and heterogeneous catalysis, the Nobel Prize laureate, Professor Gerhard Ertl, who is also on the call. And this accolade is presented by partners from the worlds of both academia and industry, in recognition of distinguished individuals and researchers in the field of catalysis. This year we are presenting the award for the 13th time. And I think I can rightfully state that the Ertl Lecture Award has gained quite a prominent standing in the scientific community, and this is evident if you look at the number of researchers and renowned scientists that have been awarded the Ertl Lecture Award, and among them also another Nobel laureate, Ben Feringa, only in 2016. Now, let me expand a little bit. Progress in catalysis research is hugely dependent, among other things, on how well we know the surface structures of carrier materials and which reactions take place on a molecular basis. And the understanding of the exact catalysis mechanism is at the heart of everything if we want to draw conclusions about structure-property relationships and we want to further develop materials. And this is why both universities and research institutes provide significant input in terms of fundamental findings and method development. But it's only the next step, in fact, the transfer of these findings into commercially available products and processes, that will push science forward as a whole, but also will accelerate industrial research. And if we look back over our 155 years history, this is exactly what we have been doing exactly from day one. BASF has been carrying out its own fundamental research while supporting others to do so. And collaborations with academic partners have always been part and parcel of what we do and played a vital role in our activities and contribute immensely to our work. And as you all know, a prime example is the development of the ammonia process in catalyst about 100 years ago, which was a joint endeavor of Karlsruhe University and BASF at the time. And we have continued in this spirit and intend to continue also in the future. That is why we founded BASCAT, a laboratory run jointly by UNICAT and BASF at the TU Berlin in 2011. So next year is the 10th year anniversary. BASCAT generates fundamental knowledge in the area of new catalytic process designed to change raw materials, and it promotes the search for alternatives to crude oil. But let's move back to the most important topic today. Let me talk a little bit more about our awardee, about you, Ulrike. Ulrike, you studied engineering physics at the TU Wien and received your PhD in physics there in 1990. In the same year, you started working as a postdoc at the Rutgers University in New Jersey, together with Professor Theodore E. Maddy. And 3 years later, in 1993, you moved to the Tulane University in New Orleans and started your academic career first as an assistant professor up to an endowed chair. That's actually the YOHO Founder Chair in Science and Engineering. And in 1998, you received your habilitation from the TU Wien in experimental physics, and this is also the place where you returned to in 2010. So full circle. And since then, you hold a full professorship at the Institute of Applied Physics and serve also as a deputy department head parallel to this position as a research professor at the Tulane University. For more than 30 years, Ulrike has been dealing with surface physics, and I think it's fair to say she is a true authority in this field. And following in the tradition of Gerhard Ertl, she first began to investigate surfaces in ultra-high vacuum using scanning tunnel microscopy and other surface spectroscopy techniques. In contrast to Ertl, however, she focuses on metal oxides. She's particularly interested in the surface structure and molecular processes that take place on the surface. She was the first to use scanning tunnel microscopy to really make atom by atom visible on the surface and to detect surface defects. In a further step, she investigated chemical reactions triggered by these surface defects and draw conclusions about the catalytic mechanism of a reaction. And in doing so, she proceeded in a particularly systematic and meticulous manner and analyzed these complex materials extensively. That was all true to the motto that it is not enough to understand the system somehow, but that it must be examined in detail from all facets in order to gain truly profound insights. Now, a special testimony to her work is, for example, the overview article, I cite, The Surface Science of Titanium Dioxide, and that was published in 2003. Titanium dioxide, as you all know, is used in many applications as heterogeneous catalyst, as a photocatalyst, is used in solar cells, or as a coating for implants. That's just to name a few. The driving force of Ulrike and her team was to better understand and improve the catalytic mechanism and to transfer the findings to other metal oxide surfaces. However, the focus was not only on the purely academic interest, but also on the question of how to improve corresponding applications based on the knowledge she gained. In 2012, Ulrike received the ERC Advanced Grant, Oxide Surfaces, for her valuable research contributions, one of the highest endowed and most prestigious research grants in Europe. Now, but that's not all. This year, Ulrike received another ERC Advanced Grant, this time for her research on the interaction of metal oxide surfaces with water. And such interactions take place everywhere in nature, but so far there are no findings on an atomic scale. And there's a reason for this. What sounds trivial is by no means so, because the usual methods of investigation cannot be used. I think it's easily conceivable that in an ultra-high vacuum, water would immediately evaporate and falsify the results. But I guess Ulrike Diebold would not be Ulrike Diebold if she had not found a solution to this problem. Using a special technique, she produces a highly pure drop of water that she can use for her measurements. And at the same time, she and her team have achieved important success in the field of high-performance microscopy, with which she can take pictures and even videos of individual atoms. And I'm highly curious to see a sample of your work, hopefully later in your lecture. Ladies and gentlemen, besides the two ERC Advanced Grants, Ulrike has received numerous accolades for her outstanding scientific achievements. And I just name a few. The Wittgenstein Prize, which is the highest research award in Austria, endowed with 1.5 million euros. The Arthur W. Adamson Award in surface chemistry. The Blaise Pascal Medal, and most recently, the Science Award of the City of Vienna, as well as the Doctor Honoris Causa of the Brno University of Technology. Ulrike is also a fellow of several societies, includes the Austrian Academy of Sciences, the European Academy of Sciences, the German National Academy of Sciences Leopoldina, and the Academia Europaea. And additionally, you have taken a leadership role in several professional societies, such as the German Physical Society. Let's now just briefly look at some numbers. She has documented her results in more than 250 peer-reviewed publications, many of them in prestigious journals such as Nature, Science, and Physical Review Letters. The number of citations is higher than an amazing 21,000 in the Web of Science with an H index of 62. And Ulrike, you have given numerous lectures, 190 invited talks at conferences, 23 plenary and keynote lectures, and that's only over the 5 last years, 130 colloquia and seminars. And these I have to say, in terms of numbers, are truly impressive figures. But that's not everything. Mentoring, coaching, and empowerment is very important to you. Ulrike, you have supervised more than 60 postdocs and PhD students, among them 12 of them who now hold academic positions in various ranks. So the group Diebold truly stands for an exceptional scientific quality. And last but not least, networking is not just a phrase for you, but comes from your heart. I learned from your fellows that you are a passionate skier beyond everything I could imagine. And how could it be different that you combine sports and sciences as an organizer of the legendary 3S Symposium? And for all of you on the line who don't know what 3S means, it is the Symposium on Surface Science. Please allow me now to add a fourth S for, let's say, skiing. And it makes sense, as this conference, and I quote here, it says, it gathers every winter the who's who of surface science for a week of brilliant science, energetic skiing, and exuberant sociability. So I guess sociability is the fifth S. Dear Ulrike, I'm really impressed by your scientific achievements, and it's my pleasure and a great honor to welcome you today to our virtual award ceremony. Now, before we learn more about your lecture entitled Oxide Surface Science, Chemistry at the Atomic Scale, I'd like to hand back to Professor Meyer, who will continue our virtual event. Thank you very much.
Thank you very much. Thank you very much, Dr. Gratz, for the laudatio. Thank you very much, Professor Thompson, for the welcome words. Yes, so now we're going to have the presentation of the award, which in the normal circumstances would be a moment where everybody comes on stage and where flowers are being handed out, and where in particular then this document as a confirmation of the Gerhard Ertl Lecture Award is being presented. It says Gerhard Ertl Lecture 2020, awarded by the Berlin Universities, by the Fritz-Haber-Institut of der Max-Planck-Gesellschaft, Uni Siscat und BASF, to Professor Dr. Ulrike Diebold, Institut für angewandte Physik, Technische Universität Wien, Österreich. It is signed in Berlin on the 10th of December of this year, as of today, and it is signed by me on behalf of the three Berlin universities, on behalf of the Fritz-Haber-Institut, Uni Siscat, and BASF. And this document I am now going to hand to Ulrike Diebold just before she starts a lecture. So I guess I'm going to bring it to Wien, and then let's see how it arrives there. That all went okay. It should be there by now. Maybe Ulrike can show if it worked out.
Here's the award. Thank you very much, Gerhard. Thank you for this lovely introduction. I'm absolutely honored to receive this award, as you can imagine. I want to thank all the jury. I want to thank the consortium for sponsoring it. I want particularly to thank Detlef for this wonderful laudatio. It's good you couldn't see me because I was blushing a little bit. And I want to especially thank Professor Ertl, for being an inspiring hero of mine for all my career. It's a really lovely occasion, and I cannot thank enough. I feel really deeply honored to be able to receive this award and also to give this lecture to you. So I guess I should start now, Gerhard?
Yes, I think with any further ado, you could just take the floor now and start your lecture. I mean, the title has already been announced several times, and it's also announced on the invitation to this online event. Oxide Surface Science, that's what it's about, chemistry at the atomic scale. So Ulrike, yes, the floor is yours, and I will only come back afterwards when there are questions. And again, everybody who's listening to the talk and who wants to put in a question, please do that by email and send us this. And I will read out the questions at the end of the presentation. Now, the floor is yours, Ulrike.
Okay, well, thank you so much again. I feel absolutely honored to receive this award and also to receive this award. And, you know, it's really a pity that I cannot be in Berlin. I had looked forward so much to join and hang out with all of you. It doesn't materialize, but on the other hand, maybe one can reach a much wider audience this way. I want to welcome everyone who is listening to my lecture. I also want to welcome the colleagues here at TTU Wien and also the students from a surface science class. We got special permission with appropriate social distancing to be here together and, you know, listen to my lecture. So let me get started. It has been already announced that I'm interested in oxide surface science, chemistry at atomic scale, and I want to, again, maybe thank, not maybe, but definitely thank Professor Ertl. So I have, you know, he was really formative in my career. I remember when I first met him, I'm sure he doesn't remember to have met me. I don't think he met me. So actually, let me tell you how that happened. So this was a post-deadline session of the German Physics Society. So the German Physics Society had post-deadline session. It was the very first German Physics Society pre-meeting I ever went to in my life. And these post-deadline sessions, if you ever get a chance, you should go there. They are really rowdy atmosphere. At that time, it was still in a pub. And, you know, it was free beer, so physicists were sitting there and drinking beer, and somewhere in the end of the room, there was, you know, a transparency using screen, and someone gave a presentation. No one paid any attention. People were just drinking beer and laughing and entertaining. And then suddenly, the room got quiet from the screen all the way back to me, and he could have heard a needle drop. And it was Gerhard Ertl presenting what then should be the oscillating surface reactions that, of course, he is also describing in his Nobel lecture. And this is a video of oscillating surface reactions. That time he talked about platinum, the oxidation on platinum 110. This particular one I've stolen from my colleagues here in Vienna. It's a different reaction, but similar. So what you see is these bright and dark features. We have adsorption of oxygen or CO, and the work function shows you what happens. So it's a real picturing of these reactions. And it was really fascinating, and you could see that time that something really was happening. And what's happening was that things were reported that when, you know, earned Professor Ertl the Nobel Prize a few years later. And there was another anecdote I want to say. So when he got the Nobel Prize, I was, of course, super excited because of his fantastic science, and I've always been a fan of that. So I wrote him an email, not expecting any answer, and 3 weeks later, very personalized, very nice letter came. And it told me that he's a very special person, not only a fantastic scientist, but also a really considerate and kind and nice person. So, Gerhard, you're my personal hero. All right. So, of course, Gerhard Ertl pioneered the surface science method. So my take on surface science, I call it experimental modeling using tightly controlled conditions. So very specialized samples, very well-defined samples, very well-controlled gas atmospheres. And the upshot is that because of these really well-controlled systems, there's a very close interaction with theoretical modeling, specifically with density functional theory, where people can also calculate slabs, 0 Kelvin in a perfect vacuum. And then because both of these systems are so well controlled, there's a very tight interaction between experiment and theory. They can really help each other and explain and discover new things. And by combining theory and experiment that way, what one can obtain is mechanistic insights into fundamental surface processes at a single molecules atomic scale. And it is already mentioned that my special interest are metal oxide surfaces. For two reasons. A, they're just there, so they're naturally abundant. And also they're quite useful, so they're relevant for all sorts of energy-related applications. Catalysis, photocatalysis, electrocatalysis, batteries, you name it. So the surface science method uses, as I said, very well controlled conditions, typically ultra-high vacuum, the pressure of 10 minus 10 millibars. So the experiments are conducted in these stainless steel ultra-high vacuum chambers that are sophisticated and expensive and cumbersome to use. But the reason is that just everything out in air will be dirty. So what I teach my students in very first lecture of my surface science class is dose of 1 Langmuir. So if you expose a very sticky surface for 1 second to a gas pressure of 10 minus 6 millibar, then it's completely covered with a full monolayer. And 10 minus 6 millibar, that's 10 minus 9 atmospheres of 1 ppb, so that's not very much. So normally surfaces are just dirty outside in air. And by putting them in this ultra-high vacuum chamber, you can keep them clean and you can really study the surface itself rather than the dirt that's on it. The other thing is that one uses single crystals, and the method of choice, especially for metal oxides, is scanning tunnel microscopy. So here, this would be a platinum 1,1 single crystal, and then you see the end of the tip of the scanning tunnel microscope and the mirror image on this highly polished platinum single crystal. And then together, one can get really nice insights. So I want to show a very early work. So this is one of my favorite surfaces in life. That's the tier 2 rutile 110 surface. On top you see a ball and stick model. You can see titanium atoms, those are the gray atoms, and the oxygen atoms who fold coordinated, they stick out a little bit. And then in the lower side, you can see an empty state system image where each of these titanium atoms is very clearly visible. And because we have this nice high atomic resolution, you can see vacancies, single oxygen vacancies as bright spots in this image. Now, very often in metal oxides, it's not the perfect surface, but it's these defects where this action happens. And for example, when you have a little bit of, just a tiny little bit of water in your vacuum chamber, then the water will come and will dissociate and will put the proton to the next oxygen atom. What I want to show you next is, here is a STM image again, in a little bit more fancy 3D representation, and this big, what looks like a mountain, is actually an OH group, the one surface hydroxyl. And I want to put your attention to this region where this arrow points to. So if you're now, I will now play a very short movie where where a water molecule will come, absorb at the surface, dissociate, put the proton to the next oxygen, and then the two diffuse away. So here, a water molecule comes, dissociates, you make 2 hydroxyls, and then they move apart. Now, admittedly, it's a very simple reaction, but these are real experimental data. So this is what they call experimental modeling. We can really see how a reaction happens step by step. So what I want to have introduced a little bit the techniques that we use, and they have pioneered by Gerhard Ertl and his colleagues. I want to show you 3 examples where I think that surface science can really make an impact. The first example is what we call single atom catalysis. So catalysis where the active particle, nanoparticle, is shrunk to the smallest dimension to a single. The second one is how we can measure very fundamental surface properties at the single atom, single molecule scale. And the third part was already mentioned, to bridge the gap between ultra-high vacuum and liquid water. Okay, so let me just very briefly introduce what we mean with. Normally, a catalyst, a heterogeneous catalyst, normally consists of a nanoparticle. Here, for example, would be a platinum nanoparticle that is put on some sort of inexpensive metal oxide as a support. Now, if you have a nanoparticle, then, and the reactions happen at the surface, then of course only the top surface atoms play any role. So everything that's here dark inside of this nanoparticle actually is really kind of useless, right? So it's really part of this reaction. And it's a sad truth that the best heterogeneous catalysts are often rare and expensive metals, such as platinum, for example. So the idea is that if you could disperse it to single atoms and put it on a surface, then maybe a single atom could be responsible for this reaction. First of all, you need much less of the expensive material, but also the single atom then, of course, is very intimately related to the support. So it will really matter how the single atom binds to the surface, and the environment of the single atom on top of the support really matters. So single atom is maybe not the right choice of words, even though that's used. It's maybe better to call it single site catalysis. So this is a little bit a controversial, very hot topic in catalysis right now, but also a little bit controversial. And I think surface science can be really an answer and impact to understand what it is. Because if you think about it, you really need to know the environment of each. And in surface science, that's what we do, right? We control each single atom and the environment really well. So because we have atomically controlled model systems and this excellent match to theory, so single atom catalysis would be an ideal topic to study in surface. Except for one little caveat. It turns out when you put one of these metals on a single crystal, which are typically our model systems, and you heat them up to the temperature where the reactions happen, then these particles don't stick, they don't stay as single atoms. What they make is they ball up and make small clusters. So unfortunately, normally the single atoms are thermally not stable on most single crystal surfaces. Now we have found a wonderful model system, and we is royal we, so I should give all the credit to my colleague Gareth Parkinson, who is really spearheading this work in our group. So I want to show you this wonderful model system for single atom catalysis that he found. I want to explain why it works. And also then I want to show you a few of these individual atomic processes and what we can learn, and what we can learn maybe more in general about single atom catalysis. Okay, so this is a result from 2012, where we looked at an Fe3O4 magnetite, an iron oxide single crystal that's shown in the upper right. It's a single crystal prepared in this special way that we have in ultra-high vacuum surface science. And then when we evaporated gold atoms on it, then we had a real utter surprise, because normally gold is very diffusive. So gold immediately makes clusters at room temperature. And this particular surface, each gold atom was stuck individually. So these bright spots that you see in this image, each bright spot is one individual gold atom that sits at a very specific site on the surface. And on the right-hand side, what you can see is the coverage of these gold atoms in monolayers. And not only are they stable at room temperature and don't move at all, they even stay stable up to 673 Kelvin, at which point these gold atoms, the density of these gold atoms goes down, not because they evaporate anything, but just because they aggregate to these clusters. So this is thermodynamically most stable phase. We were really intrigued by this, and it took us another 2 years to really figure out why. And it has to do, of course, with the atomic scale structure of this. So this is a ball and stick model, very well confirmed. We know this structure precisely from LEAD-AV. How this surface looks like. So you have these rows of iron atoms and oxygen atoms. And the key thing is, and that's why it took us a while to figure out what it is, underneath the surface there's some well-ordered iron vacancies. And because of these iron vacancies in top view, you get special sites. So here, between two oxygen atoms, you have a special adsorption site. If you put the gold atom there, this is where it will stick. Sure enough, you put the gold atom here, it will be cationic, so it will give off some of its charge, and it will stick exactly to the site, and the next one, 8.5 angstroms away. And they're bound so strongly that they don't move at room temperature. Now it turns out that this is not only true for gold, but Gerhard and his friends went pretty much across the periodic table. So they were very busy and put essentially all elements they could find, and for each and every one of them, you could see single atoms at especially this site. That's a really wonderful model system, and we understand why. We can put and place single atoms on a well-defined support. Now, the next I want to show you a bit of results of platinum. So if you take platinum atoms and put them on the surface, I already mentioned platinum is good catalyst, for example, for CO oxidation. So this here is a thermal desorption of carbon monoxide. So carbon monoxide is very often in surface science a very simple test molecule to study relatively simple catalytic reaction. What you can see on this plot on the x-axis is the temperature of the sample. Room temperature up to 600 Kelvin as it is heated up. On the left-hand side, you can see how much the carbon monoxide is dissolving from the sample. It's called thermal desorption. The gray curve on top is from the clean iron oxide surface. So there, CO doesn't even stick at room temperature. And these other traces is when you put just a little bit of single platinum atoms. And you can see CO desorbs at a certain temperature, but not only CO, but also CO2. So the CO reacts and makes carbon dioxide. And it turns out by taking an oxygen from the lattice, that's called the Max-Planck-Gesellschaft mechanism. We know that from isotopic labeling. We can monitor the reactivity of these single atoms, but we can with STM also look what happens. So this is a STM image. That gray one is an STM image that's taken at room temperature. On the left-hand side, you can see the calculated configuration with density functional theory. And what happens is when you put the CO molecule on top of it, the CO interacts. So it lifts this platinum atom out a little bit. It's an asymmetric configuration. Because it's asymmetric, it can be asymmetric in one side or the other side, or one side, the other side, one side, the other side. So it actually at room temperature, it wags back and forth. And then this hamburger type thing, this two-lobed thing, is because the CO wags back and forth so fast that the STM tip cannot even follow. How we know that's true? Well, it can just cool down. And then if we cool down and take STM image at low temperature, we freeze out this motion. And then if we increase the bias voltage in our STM a little bit, then you can see this streaky part. That means that we started making this wagging motion and initiated that with our STM tip. Okay, so that's just one single atom, platinum atom. And we know how it looks like when CO is adsorbed. Next, I want to show you a movie. It's a movie that ran pretty long movie, long times. It ran 41 frames, several hours. And I want to show these bright spots here again, platinum atoms. The rows are the substrate. And I want to show what happens when you open a valve on your ultra-high vacuum chamber and leak a little bit of carbon monoxide. So what happens is you see some mobility, and then many of these double-lobe features that I explained to you just a minute ago start to appear. So clearly the CO adsorbs, comes to the platinum and lifts it out a little bit, so it will also start to move around. Okay, now I want to play this movie again, but I want to draw your attention to this spot that's in this rectangle, because what will happen is that this one platinum atom that already has a CO, so it looks a little bit like this two-lobe thing. The second platinum atom will also catch a CO, it will mobile, and again, at some point, it will start to merge and form a dimer. So here you can see the partner platinum carbon will come together and form a platinum dimer. And without looking what happened, you would never have guessed that this is a platinum dimer. It turns out, actually, if you put enough CO on the surface, most of these platinum atoms will not stay single atoms, they will come and become these dimers. And we can see them quite nicely with non-contact AFM. So because we know so well how these platinum dimers sit on the surface, we can also model how these platinum dimers react and how, when it desorbs, it takes off an oxygen from the lattice. This is work from Matthias Meyer, where he tried to model with density functional theory from first principles this process using all the information we gave him from experiment. This is what he came up with. So here's the platinum dimer, and then one of the CO molecules catches oxygen from the substrate and desorbs it, carbon dioxide. Now again, I want to play this movie again, and this time I want you to pay attention a bit to the surrounding of these platinum dimers, because you can clearly see how the substrate reacts, how the iron oxide reacts, how it changes and makes one oxygen atom reactive, and that's the one that then is desorbed off. So it turns out that these platinum dimers bring reactivity. So in this CO2, the TPD trace that I showed before, we saw this carbon dioxide coming, and it desorbs at a temperature that's consistent with this theoretical model that we developed. Unfortunately, it's a really, really lousy catalyst, because if you put CO there and run it once, then CO comes, and then if you do it a second time, then actually these platinum dimers have then the CO will desorb lower, and then there will almost no carbon dioxide anymore. And the reason is that there's less and less of these platinum dimers. They have balled up and became bigger clusters. And these clusters will be less reactive for the CO2 oxidation for two reasons. First of all, they need to take the oxygen from the substrates. If a cluster is less in contact with the oxide substrate. But also, if you pay attention, these curves are shifted to a lower temperature. So the CO2 desorption needs a certain activation energy, and when at the time the CO desorbs from the platinum clusters or at lower temperatures, there's still no CO2 anymore, carbon monoxide there anymore due to this reaction. Now, from these TPD traces and from the temperature that one, I think my movie's, okay. One can actually derive desorption energy. So what is the energy that's needed to desorb? How well are these CO molecules stuck on the surface? And there's more or less sophisticated ways how to do that. People have dealt with that for a long time. And in fact, people have studied CO desorption on metal single crystalline surface for a very long time. Now, this is a list of all sorts of papers that we have looked through. That is a part of the reference list of a paper that we just got accepted. We looked at different elements from copper, silver, gold across the periodic table to iridium, metal 111 and metal 110 single crystals, and what people reported as desorption energy. And in this list are some of the heroes and big giants of surface science. It turns out that people have dealt with this for a very long time in very great detail. So why have people paid so much attention? Well, the adsorption, how strong the CO is adsorbed on the surface, or any molecule is adsorbed on the surface, is a key concept in catalysis. Because if it's adsorbed too weakly, then it cannot react, it will desorb too quickly. There's a low reactivity. But if it's too strong, then it cannot go off once the reaction has happened. That's called catalyst poisoning. And there's a so-called Sabatier principle that you try to be at the right sweet spot between the desorption temperature. And this can be explained, all this data can be explained quite nicely in the so-called deep end model, where you look at the interaction between the metal deep end of these transition metals. So the question, of course, is how does this, what we know and accumulated the knowledge on metal single crystals for a number of years, how does this relate when you just put one single adatom on this? And here's where Gareth and his students and postdocs come in. This is the fruit of very long work. This is TPD traces of metal single metal atoms on Fe3O4. All these different color traces is how the CO desorbs, and wherever there is an arrow, this is where the CO desorbed from single atoms. Now, the expert might know how do we know? And we always combine different experiments. For example, XPS, we can clearly see how the XPS peak shift shifts. And then from these desorption temperatures, we were able to convert this into desorption energies and plot them together with what's known for this metal single crystal. So it's clear that the single supported atoms are deviate quite from these metal single crystals. It's not a real surprise. The question is how we can figure out what happens. And again, because we have such a well-controlled system, we can combine this with density functional theory, and the colored, the squares are the theoretical results. And there's really excellent agreement between theory and experiment, except for the platinum, and we know why already. And you know too, because that's where we have platinum dimers instead of zinc. Now, I don't want to go into detail here. I just thought there's a long analysis how we can understand this behavior in detail. So we can compare the adsorption, the metal, and then on a metal oxide surface, or even metal oxide surface. And then we can figure out why sometimes adsorption is stronger and sometimes less, and how the substrate really plays a big role. Maybe let me just point out one interesting aspect. This is this one, iridium. So for iridium, the desorption temperature, the adsorption energy is much, much higher. And in fact, it behaves, the single iridium atoms behave really like an iridium oxide substrate. So iridium is obscenely expensive and absolutely rare, but at the same time, the absolutely best electrocatalyst. So this suggests that maybe supported iridium metal atoms could be really good electrocatalysts. Other things we have learned is depends how these metal atoms sits on the surface, how the ligands are oriented. So I don't want to go into all these details, but we've learned quite a bit on how it's different between a metal atom and a metal single crystals. And I think by coming to these very detailed studies where we can really know from many different methods how the surface reacts, how the atoms sit there, and then combine it with theory, we can really come up with some sort of new chemical intuition that hopefully helps in the end to design better single atom catalysts. Okay. Second example. Quite different. Measuring fundamental surface properties at the atomic scale. I guess it has to do with, looking at things in a different way. Now, there's a method that's kind of the hot new kid on the block in surface science, this non-contact atomic force microscopy in ultra-high vacuum. Atomic force microscopy is a very well used technique, but in ultra-high vacuum, it's only the last 10 years or so, it's really taken off thanks to this Q+ sensor that was invented by Franz Giesebel from the University of Regensburg, where one mounts an STM chip on a piezoelectric tuning fork that oscillates with its own resonance frequency with a very high quality factor. And then by bringing this STM chip close to the surface, measuring the resonance frequency, and then taking images of this resonance frequency with extremely high resolution. This is a very famous result by Leo Gross and colleagues from IBM Rüschlikon, where they put this pentacene molecule on, so that's shown in panel E, a pentacene molecule on a surface. In panel B, you see the best STM image you can ever get. It looks fuzzy because what you see in STM is essentially the orbitals. In panel C, you can see the frequency shift that really shows you the molecule like the chemists are drawing it. That's a fabulous way of measuring, of taking images on surfaces with, I would say, the ultimate resolution. Now, key is not only this Q+ sensor I mentioned before, but key is also what Leo Gross and colleagues started doing. So at the very end of the STM tip, they mounted a CO molecule. So they functionalized it with one single CO molecule, and then you can take this really fantastic images. So our idea now was to use also a molecule on the surface to probe single surface hydroxyls. I mentioned before, you have hydroxyls, you have OH groups on the surfaces. They're really important in catalysis. And the key question is how strong is the proton bound? How easily can it be given off in hydrogen or dehydrogenation reactions? And the key word there is proton affinity or surface acidity. Now, the normal way this is done is, for example, in zeolites, by measuring acidity, is absorbing the whole, flooding the whole material with molecules, different molecules with different type of molecules, measuring the heat of absorption, and then extrapolating the proton affinity that way. The idea is to take a molecule, just one, and place it on another OH group, and then doing this kind of force distance curve, so coming in and out, and measuring the force between one OH on the end of my STM tip and one OH on the surface, and finding out how strong the OH is bound that way. Now, the surface that's drawn here is actually the one where we did the experiment. It's an indium oxide one on one surface. I don't want to go into any details. The queen of indium oxide is Margareta Wagner in my group. Just let me point out to you that on this surface there's 4 different types of oxygen atoms. Different types in the sense that they all have a different coordination and they all have a different kind of coordination to the neighbors and bond lengths and so forth. So these 4 different oxygen atoms we call alpha, beta, and gamma. All of them have a different electronic structure. So this plot here shows the valence band, the density of the local density of states. The different colors is for the different oxygen atoms. And we can see maybe the red curves is shifted towards 0. Here is the valence band maximum. So this one would be the most reactive one, would think, and the others would be less reactive. So we expect a different proton affinity, how strong this proton is bound on each of these different. And that's what we want to probe with our force microscope. So first we need to hydroxylate it. The way we hydroxylate is similar I showed you before. Margareta exposed some water. The water dissociated mode OH group on the surface at some special sites. And then she was able to take this proton with the tip and snap it and move it to another place and move it to all these different positions. And that way make 4 different type of OH groups on this surface. And these here are then these so-called force distance curves where the tip goes in and comes out again, and one can measure the short range force between the very end of the tip and the surface. And you can see that these force distance curves, there's 4 the black, the red, the green, and the blue are the 4 different types, and each one of them is on this different surface hydroxyl. So it's a very characteristic feature that we see. Not only an experiment, we could model that really well with theory as well. So there's really quantitative agreement between theory and experiments. So you can measure the force between one OH on the surface, one OH on the tip, get quantitative agreement with theory and experiment. Very nice. But the question is, how can we get a number that we can get the chemists, how we can convert this to something like proton affinity? And here I have to give full credit to this ingenious theorists from F.O. Erlang and Bernd Meyer. What he did was he just calculated with the same type of tip on 3 gas phase molecules, these force distance curves, and probed how the OH group moves there. And it turns out that one takes this force minima and plots it against the tabulated proton affinity, you get a wonderful straight line. So this now we use to relate the force measurements to proton affinity. We take our experimental curves. We look where is the minimum on our force curve. We put the minimum, we find the right value on the y-axis, and then convert that to this linear curve to a proton affinity. We can do that for one type of oxygen atoms, the second type of oxygen atom, third one, and the fourth one, and so on. So this is really interesting because we can for the first time assign to one type of hydroxyls a special one-side proton affinity. There's no calculated values to compare that to because the DFT people will appreciate it's not easy to calculate something that's a charge system. What we can compare to, though, is change in proton affinities, and those agree quite well. And to top it off, we've been able to not do that for one specific surface, but we used the same type of tip also another oxide surface, this type, the TO2110 surface, and got the proton affinity that way. So I don't want to go into any more details here. What I wanted to convey here is that we have found a novel way to evaluate surface hydroxyls one by one at regular sites, but of course it opens up the opportunity to look at the interesting parts, its steps, its defects, dopants, and so forth, which also works on insulated materials. And the new ERC grant that I've been granted will look exactly into this fact, look and try to make this into an actual measurement. Okay, last example, bridging the gap. So that's a big theme in surface science, has been for a long time, right? I explained to you that with ultra-high vacuum, 10⁻11 millibar, but catalysis is done at least at ambient pressure, sometimes at high pressure. How we bridge this gap, how we bridge what we see under these very idealized conditions to something that's what's called realistic conditions, and that has kept parts of surface science busy. And for gas phase, I think there's very well developed techniques, but for doing it with liquid water, then, it's a whole other ball game. So I got this movie here from my student Matthias Müller last night that kind of, I hope it plays, that hopefully reminds you why we use ultra-high vacuum in the first place. It was playing around with a CO2 single crystal. You can see it puts in a beaker and takes him out again. And then what you can see is there is this little water droplet that's perfectly round. Why? Because this is where you had the surface protected, so it was UHV clean and you protected it, so it's really clean and hydrophilic, versus the rounding was just exposed to air for a little while. It became really dirty and hydrophobic. Okay? So that's why we do these things, to keep things clean. And I told you the cleanliness requirements are quite stringent. But we have a problem, right? Because if you look at the phase diagram of water, then liquid water only exists above the triple points, above 0 degrees C and 6 millibar, and in range where ultra-high vacuum is, you only have solid or liquid, solid or vapor, nothing else. So what you have to do is, if you want to put water and oxide, you have to take it out of the vacuum chamber and do it that way. It's just no way we thought of doing it inside. And one of my former students, Lan Palaika, was exactly trying to do that because the CO2 surface that I alluded to before, there were reports in the literature, when you put it in liquid water, it changes it. They put the liquid water on the surface and cleaned it, characterized in ultra vacuum, put it with a pipette, a drop of water, and put it back in and looked. So it looks like a simple experiment, but he went to great lengths to make it really clean. So he made sure there's clean water, clean gas, pumping, and so forth. And the question was, is the procedure controlled and clean enough? And unfortunately, the answer is no. So this is STM images. On the left-hand side, ultra-high vacuum prepared in ultra-high vacuum, and on the other side, in the middle, after putting liquid water liquid drop of liquid water and putting it back in the ultra-high vacuum chamber. And there's what's called the 2x1 superstructure. That's not only seen by Jan, that's also seen by other people before, and explained with all sorts of explanations, which turn out all true. In the end, what happened was just, even though Jan was very careful, the surface got dirty. And you see that in XPS. So on the right-hand side, you see the carbon-1 spectrum with a clean surface after putting the water with the pipette. And then as a control experiment, when you just have one monolayer of formate. On the left-hand side, you see the oxygen rest. And it turns out when you just put the surface in air, there's carboxylic acids in the air everywhere, and they absorb on the surface and make formate and acetate that absorbs in a bident fashion. It makes this really nice, well-ordered type of. So then Jan and and other people in my group came up with this idea on how to dose water, liquid water, in an UHV type environment. So there's a UHV chamber on the left-hand side. If you look where this arrow is, if you look in there, you see the end of a cold thing. It's a cryostat. We evaporate water. Water freezes out at the end of this cryostat and makes ice. Then we open the chamber. We put the sample in. We close the valve. We let the ice melt. Now it's only in contact with its own vapor pressure. That sometimes the ice melts and the water drops down on the surface, and then we let it evaporate, we pump out, and at some point take the sample back out again. So this should be way cleaner because the CO2 sample has never been exposed here, the water has never been exposed here, and the water is transferred as a vapor. And sure enough it is. So this is the same results I showed before. First clean, then after the pipette, and then when I do the same thing with what we call the cold thing, we have a very clean way of putting this water on the surface without contaminating it, where we can even do atomic resolve the STM afterwards. So we go from there. Now, in my group, we have several people working on testing the stability of all sorts of oxide surfaces in neat water. We add gases, and we have ways of adding electrolyte. At least we think of novel ways to do that in ultra-high vacuum conditions. Because in the end, what we want to do is photoelectrocatalysis under as well controlled conditions as we can do heterogeneous. So with that, I want to end my talk. I hope I have given a little taste where surface science is can really make an impact. So in terms of heterogeneous catalysis, where each atom matters, we can develop, a key thing is develop new tools that gives us new possibilities of looking at surfaces a new way. And then we always try to bridge the gap between well-controlled conditions and things in this. Of course, I need to I end my talk with thanking all the people that have been part of this work. So this is a photo of my group. I want to point out Michael Schmidt, who stands here in front of the Stephansdom, my dear colleague and friend, and the person who is responsible for the quality of the work. I've mentioned a few names here already on the left-hand side. There's people we collaborate in theory, and Martin Sedwin, who is in the left my group, who is the AFM expert and the source of the funding. I want to thank all of my group that have worked with me recently, that have given me the chance to present the results now. And I also want to thank all the postdocs and students and colleagues and friends that have contributed that I had fun doing science with in the last 30 years. I want to thank you for your attention. Thank you.
Thank you. Thank you very much, Ulrike, for a brilliant, very nice talk. So fitting in the whole line, in the whole series of presentations that we have had in the Gerhard Ertl Lecture Award series. The flowers that you actually gave, we had to organize that. I hope they still came as a surprise to you. We had to organize that. They are on behalf of us here in Berlin, the Berlin Universities. Good. BASF. And there are some things that need to be done. We need to do it virtual, that are without you knowing it. So we had very good contact with your technical staff. Thank you very much.
Okay, thank you very much. Thank you.
So there is a possibility for people to ask questions. We said where questions can be sent to us, and I will read that to them. Some questions are coming up. I really enjoyed very much your talk. I'm fascinated by the results actually that you saw on relating the force measurements to the proton affinity. I think that's really something spectacular. And you actually started your talk with telling how you first met Gerhard Ertl, and you said probably he doesn't remember that. I can just tell you from my own experience. You'll be amazed what Gerhard Ertl remembers. And so let's look at the questions that came in. I do not know who asked the questions, but it's also not so important maybe because I don't see a name added. But I'm just going to read the question that I see here. On page 22, within the rectangular box that you showed, I think that is the short movie that you show. I saw 2 platinum plus CO, so 2 white dots meeting together, then joining to be 1, a white dot. Why only 1 dot size showed up after the 2 dots merged?
Okay, yeah, that's a good question. So the thing is that these we call them hamburgers. So these little bilobe features come explained because the CO is whacking back and forth so fast that the STM cannot follow. That comes because of the asymmetry. So the platinum stands like this. Here's the CO, and it can be to the left or to the right. Once you have 2 platinum atoms, then they have a more well-defined position on the surface. And if you put a CO on both of them, they don't have this degree of freedom anymore. So it looks like much smaller because they're much better confined.
Okay, so maybe if I may, just from my side, I mean, connected to that, you showed that these 2 platinum atoms coming together, and you said this is then a platinum dimer. You wouldn't have known it if you wouldn't have seen how they formed. Later, you discussed that you also see their platinum clusters. How do you recognize the bigger platinum clusters on the surface?
So yeah, unfortunately I cannot go back my thing, but
That's fine.
Yeah, what we can do is so people make the size selected clusters, we call it, I don't know, so cluster that formed, size formed clusters. So if you watch this movie, right, then we can see how they come together and we can distinguish 2 or 3 or 4 and so forth. In fact, if we did that before we had the non-contact IFM, it turns out with the non-contact IFM, the resolution is much higher. So these platinum dimers I showed you, with the non-contact IFM, you can actually see sometimes 2 or 3, even 4 platinum atoms with CO molecules on top of it. Okay.
I actually see now that the first question was asked by Kun Zhao. And Kun Zhao asked also a second question, a small question, relating to the last part of your talk. How was the ice formed? I missed that part of the presentation.
Oh, the ice was formed. Okay. So what you do is so this is what we call this cold finger. So it's a little cryostat where it's cooled with liquid nitrogen, counterheated from the top. The end is cold. It's at liquid nitrogen temperature. And then this is in ultra-high vacuum. One closes a valve to the main chamber and then opens another valve, puts in water vapor. The water vapor comes and freezes at the end and makes this icicle. And then once you have frozen enough water vapor, you close the valve, you have an icicle, and then you put in the sample in. The vapor pressure is very low at these low temperatures. You close the valve, and then you turn off the cooling, and the thing heats, and then the water drops down. Oh, sorry if I haven't explained it that well. Mm-hmm.
Okay, thank you. Thank you very much for that. So the people that saw this via in being streamed, they could only ask the questions by sending us a message before that. There is a small group of presenters that we also made the photo shoot with in the beginning. They can ask the questions themselves. And so Detlef Kratz would like to ask a question. He can, in principle, ask the question himself. We will switch the video on. We will switch the microphone for him on. It might take a few seconds. Then he will ask his question to you himself.
Yeah, thanks, Gerhard. Can you hear me?
Yes.
Yeah, okay. Ulrike, great talk. Really fascinating to see what you can do with some really excellent technical facilities and really going, as I mentioned, into in-depth. And it's mainly my question is related to the question just before about the dimers. And you showed wonderful structures of these single atom structures where you have singled out the atoms and depending on the temperature, they then agglomerate. Do you in fact, and that was related to the other question, see whole structures where you only have dimers? Because many of the catalytic reactions actually do not work on one single platinum or palladium or iridium. They typically sometimes work together. Mm-hmm. And I was wondering whether you have actually pictures of dimer structures being catalytically active. And so a whole system kind of that forms only dimers, maybe even trimers, because this is, it's a different, if you have whole, clusters of atoms, they work differently to the single one or the double ones or the triple ones. Similar to homogeneous catalysis.
Mm-hmm. So that's why we were so intrigued with these dimers, right? Because the form, and it seems that the dimer is a very stable feature. So as long as you don't heat it up, they don't even agglomerate more. And this seemed to be quite reactive in our, so we didn't do any more catalysis than CO oxidation, I'm sorry, okay. But you're absolutely right, the dimer is more important or more relevant perhaps because, we could think more relevant because if you want to have a reaction that's not just yanking out an oxygen from the substrate, right, then you really need to have a second ligand, second molecule on top of it also. Now, it turns out some of these metal adatoms, for example, rhodium or iridium, they like to be in a configuration where they like to have 4 ligands. So in fact, those are the ones that very easily form a dicarbonyl. So you could think of putting on rhodium, for example, not only one, but a second molecule on one single atom, and then try to make a reaction that way. And Gareth and then Manuel, one of his students, try to figure out if that's actually possible for rhodium atoms and look at one model reaction that way.
Mm-hmm. It will be interesting to see. Thanks.
Thank you.
Okay, then I continue with a question that has come in from Volkmar Koller. And he asked, while investigating hydroxyl groups / water under UHV conditions, how do you cope with water contamination from the UHV background?
Yeah. So we pride ourselves. So I'm not sure I exactly understand the question, so let me try to, answer what I should understand. So why we do it under vacuum is because we have this ultimate control, right? We have single hydroxyls and we know exactly at what position these hydroxyls are, and we can even put the proton from one to the other with this STM tip. So that's a wonderful way of making a well-defined model system. Now, in our vacuum, so 10 minus 11 millibar is actually not such a good day. We pride ourselves of having really, really low vacuum, and where water is one main component, but not very common. So normally the vacuum the pressure in our vacuum chambers is so low that water contamination is really not a problem. Of course, when you open the valve, you can put water vapor with a well-defined dose, and then hydroxylate our surfaces that way.
Okay, thank you very much. Another, or actually 2 questions asked by Yun Liu. And this question actually starts with explicitly saying, thank you for your very nice work on CO absorption. I'm sure that normally all questions would have started with thanking you for a very nice presentation. But just the short version that the questions get in, they mostly immediately go to the point. And so the question here is, do you have any idea about the interaction between the dioxygen molecules and single atom catalysis on iron oxide? So this is on the CO adsorption on single atom catalysis, right? I mean, this part.
Dioxygen?
Do you have any idea about the interaction between the dioxygen molecules and single atom catalysis on iron oxide?
The dioxygen, I'm not sure I do understand this.
Okay, then maybe I immediately go, maybe it can be clarified. I go to the, because this is
I'm happy to answer any question by email, so just Google me, okay?
Yeah.
And send me an email. I'm happy to come and discuss that way. Mm-hmm.
There's another question by the same person. So for platinum and iridium single atom catalysis, why did this single atom have such a strong binding with the CO?
Yes, so that's a good question. So there's many things involved, right? So one is, for example, when you have this, so I mentioned that it's cationic species. So that means that the d-bed center really moves down quite a bit. That makes it much more reactive. That's a simple answer. So, in fact, in the paper that we just about published, we went through each of these individual things and tried to understand what plays a role. Does it play a role, the electronic structure? Is it the environment? Is it how this one changes, how it changes when you put the thing on? So by going through all these different details, we can then identify for each of the different individual adatoms what makes the binding so strong or weaker than for the normal case.
Okay, thank you. There's another question without the name, at least I cannot see it, and that asks about the how relevant it is to use the scaling relation of force versus proton affinity of gas phase molecules to fit the surface absorbates to it. I mean, how you exactly did that, I guess. That's the question.
So, I mean, there's no way to measure it, right? So it's brave. I agree, right? So, I mean, I showed this nice straight line, right? So there's a scaling relation, and scaling relations are good when they're linear. So between these calculated force minima of gaseous molecules, calculated with the same tip that gives exactly reproducible results on the surfaces, we get this wonderful straight line, and then we just say, okay, this is how we assign it. That's a very low way to do it. We were skeptic if it works. The only way we can tell is, as I mentioned, is that we can say that the differences in proton affinity is exactly what we would expect. So I think it's a new way of thinking of it and a new way of doing these things. In some sense, yes, in some sense, no, because one uses different molecules also in other cases, like I showed the zeolites, one really looks at this acidity, so weak adsorption or weak interaction or strong interaction. One probes different gas phase molecules with acidic sites on the surface, just in a very different way than we do it with one single molecule on the tip.
I found also the relation that you showed in the plot very compelling and very nice. And so Jeffrey Poon asks, referring to slide 29, I don't know if you can see slide 29, it was highlighted on that slide that platinum, that a larger discrepancy between theory and experimental values are there due to dimer formation. Wouldn't this be equally likely for other 5D metals also, like gold, for instance?
No, so I mean, yeah. 29, thank you. One more. Next one. So these colorful circles and squares are, the circles are our data, and the squares are calculation from Matthias Meyer on single atoms. So to be consistent, this is all done on single atoms, and then for this platinum, we know that what we have is the desorption not from the monomer, it just doesn't exist anymore because we put the aggregate to these dimers. So this is actually a little bit artificial, so we could equally well have put in the CO desorption from the dimer, then would be much better agreement. But just for consistency, it's all calculated single atoms. Does it happen for others? The answer is no. So actually for palladium, there is no experimental data point there because palladium is even worse. If you put CO on palladium, it starts to not make dimers, but immediately make much, much bigger clusters. For rhodium, it doesn't happen. For rhodium, we can put CO, and it doesn't make this aggregation. So I don't think it's generally true. You have to read it in each individual case and see, and we can with STM see if they aggregate together or not.
Okay, thank you very much. There are more and more questions coming in, but as you said that you will answer also the questions that you cannot answer now, you'll be happy to do that by email. I'm just going to make a selection of a few questions that are still there, also in view of the time. So Albert Bruy, or maybe I should say Bruix, asks, what are the differences between the interface between the catalyst and water in an, and now it's gone, between the catalyst and water in an electrocatalytic cell and the interface between your sample and the thin film of water?
Yeah, very good question, actually. So we just published a paper together with Olaf Magnussen from Kiel, where he looked in situ in electrolytical cells on this Fe3O4 reconstruction in an electrochemical environment, and he saw that this surface reconstruction actually survives and stays there, and even under relatively harsh conditions for oxygen evolution reaction from the surface exit diffraction, one could see that it's still there. So that's exactly the question we want to answer, right? I mean, the first step for us is to need water. Second one, as I mentioned, is we put gas. And then, of course, we really want to do that with an electrolyte. I think we have to go the next step. So that's what my and Gareth's ERC grant is about, to try to make new ways to do that under extremely well-controlled conditions and under UHV comparable conditions.
Okay, thank you very much. I am going to ask one last question that came in. The question from Sebastian Oehner, and he asks, have you measured the hydrogen bonding strength or CO adsorption on amorphous oxide surfaces? Reactive interfaces in electrochemistry often exhibit amorphous oxides, which seem to be essential for the reactivity.
The answer is no. We haven't measured it, right? There's very hot new data. Actually, they are just, still in review at the journal. In principle, with STM, one should be able to measure, or with AFM, amorphous structures. Not so easy. What you have to have is very flat surfaces. They still have to be quite ideal. I think something that you just make under electrochemical reactions, and something that it's very ill-defined, is very difficult to get this detailed molecular information out of it. So I think the short answer is unfortunately no.
Okay, thank you very much. As I said, there are several more questions coming in, but we will actually forward the questions to you, so they can be addressed like that. I think with that, I'm very happy to see that everything worked out so nice, that the handing over of the document from Berlin to Vienna worked out excellently, that even the flowers arrived. I'm also very happy that all the technical things that I need to work out worked out. The vision, so the quality of the images and also the quality of the tone was simply excellent. We actually zoomed in when you showed this slide where you had a whole list of references where you quoted all the work that had been done in the field. We actually zoomed into that. The quality of that is really excellent. I'm also happy to say, and you will also be happy to hear this, that we looked at more or less the middle of your presentation at some point, how many people were following live the stream at that moment. And at that moment, it was 341. And so this number of people would not have fitted in the lecture hall in the Harnack House. And so if there is any advantage to be thought of in this situation that we're in, is that we learned to deal with more complicated situations, that we learned also to set this up from a distance, that it indeed enables even more people to participate in these fantastic lectures than otherwise would have been possible. And so with that, I think we bring this part to an end. We will briefly meet later in a small group to discuss a little bit how it went and what the experience is to do the Ertl lecture in this way. I really want to thank you, Ulrike, once more for a very nice presentation. I also want to thank the technical staff on your side for helping in getting this organized. I want to thank the technical staff on our side to get it organized. I want to thank everybody who joined in to this event. Of course, you can also look at it afterwards. You can also look at it yourself afterwards if you want. And of course, we're all looking forward to being able again to hold these events in the way we would like to hold them, namely coming together in one location and also sharing thoughts and ideas before and after in meetings. We all hope that will soon be possible, but up to that time, we had to do it this way. Thank you very much, and I would say goodbye. Thank you for everybody attending, and goodbye. Maybe you still want to say one last word, Ulrike, but then we're going to close.
Yes, I want to thank you. Thank you for giving me the opportunity. Thank you for, organizing everything so nicely. Thank you for the award. Thank you for the technical staff here and in Berlin. And thank you for my surface science students for coming and listening and giving me the, necessary feedback here in the room. Thank you. And thank you, Gerhard, for being such a wonderful role model for me. Thank you.
Thank you very much. And I'm looking forward to meet soon in person again. Bye-bye.